This meeting is being recorded.
In section 12.4, we will look at another method to prepare alcohols. So we've already seen both substitution, SN1, SN2, and addition reactions of various forms. Now we're going to take a look at a reduction to form an alcohol, to prepare an alcohol. So we can reduce a carbonyl. So hopefully you recall after a discussion of functional groups, what exactly a carbonyl is. So we have that carbon oxygen double bond somewhere in our compound. So things like aldehydes, ketones, esters, we can reduce or change the oxidation state. So that CO double bond will then become an OH, right? Bond to whatever the rest of our structure is. And we use this term oxidation state as a method of keeping track of, how many electrons are attached to which atom. So we refer to commonly the oxidation state of carbon, going from one to another when we perform things such as reduction. So we'll do a quick review of how to use formal charge to determine whether or not we are performing a reduction or an oxidation or neither. So each atom is assigned half of the electrons that it's sharing with another atom because these are covalent bonds, right? Because of covalent bonds with these compounds. And then we can figure out what the formal charge is on the carbon. Let's take a look at methanol specifically. So we have methanol here shown, right, in this view here. So we've broken all the bonds. We've given carbon 4 electrons, each hydrogen 1, and then our oxygen, we've given 1 from the 4 bonds that surround, right, our carbon here. So we've broken homolytically all of these bonds, and that's what we see here. So our carbon, we could do this another way. We could treat all the bonds as ionic, and we would have this result here. So then carbon, it would steal, right, all the electrons from hydrogen. These would be H pluses now, and carbon would have 6 electrons. And in this case, oxygen would steal the electrons from the CO bond. So we broke all of these bonds heterolytically based on electronegativity. The carbon received all the CH bonds, and then the oxygen received the CO bond. So what we see here is that carbon would have 6 electrons if we did it this way. It would have 4 electrons if we did it this way. Either way, we would come to a conclusion that the oxidation state on the carbon in methanol would be -2. So how do we come to this conclusion here? We take a look at our compound as a whole, and we can solve for carbon's oxidation state, right? So we can say that it has a net charge of 0. We have 3 hydrogens. Each hydrogen has a +1 charge, right? So that's from our 3 hydrogens. So 3 plus carbon, we would have 4 hydrogens rather, right? Because there's a total of 4, plus our carbon, which is unknown oxidation state. And then for oxygen, we always know in compounds it has a -2 oxidation state. So using this math, we see that 0 equals carbon plus 2. So if we were to rearrange this equation here, we could see that carbon has a oxidation state of -2. So in general, carbon's oxidation state can range anywhere from -4 to +4. So that's how, if you want to know, did a reduction occur? We know that if the oxidation state of carbon goes down, the oxidation number, rather, of our carbon goes down, then we had a reduction. Another generalized way to look at this is, are we lowering or reducing the number of CO bonds as we do from going from a carbonyl to our alcohol here? That would be a reduction in as that would be an obvious way to see a reduction as well. So we reduce the number of oxygen bonds or increase the number of hydrogen bonds is generally seen with a reduction. So we have whatever reducing agent used here. The that itself is oxidized, if you recall, and then our substrate, our carbonyl, in this case, it looks like either a ketone or aldehyde, this will be reduced, and then we see our alcohol results. So we have an addition reaction across this pi bond, right? So the reduction of the carbonyl overall adds H and H across that pi bond at the same time. So we can also prepare alcohols. Another reduction would be through what's called catalytic hydrogenation. So we can use our catalyst, platinum, palladium, or nickel, and then hydrogenate that double bond. But this is not useful because of the high temperature and pressure that's required. So that's less likely seen than other methods. Let's take a look at some more reduction here. We could use, there's 3 reducing agents that can be used to reduce our carbonyls now. So we have sodium borohydride, that's this shown here. Solvents that can be used such as ethanol, methanol, or water. And we generate about 90% yield of our primary alcohol product here. Or I'm sorry, this would be a secondary technically, right? Alcohol here. So there's other reducing agents. So we talked about sodium borohydride being a source of hydride. We see this mechanism shown here. So here's our borohydride. And then the sodium counter ion is also there. But this hydride will perform a nucleophilic attack at this carbon here, which is slightly positive. So that's why it seeks that out as a nucleophile, the H negative, and then that shifts those electrons involved in that pi bond up to that oxygen. So we generate this alkoxide intermediate here. Then we protonate through proton transfer. So we have our methanol solvent used here. We have our proton transfer. Remember, that's always a 2 curved arrow mechanism. And then we generate this alcohol. So depending on your solvent, that's your source of proton transfer. There are other reducing agents that we'll take a look at throughout the chapter as well. So lithium aluminum hydride is another. So we keep getting reminded that there's multiple reducing agents, but again, we see sodium borohydride, and we see our carbonyl here, and we have this unsymmetrical ketone, right? We have 2 different R groups, right? R1, R2. To keep track, we have 2 different R groups. So we know that it's this unsymmetrical form. So what happens is that when that nucleophilic attack happens with an unsymmetrical ketone, it will be reduced and produce a new chiral center. So we generate a pair of enantiomers, right? Our stereoisomers that result. One would have R, one would have S configuration, and then that's shown down here. The rationale is because that nucleophile could attack from either surface, either side of the plane that the carbonyl is in. So make sure that you note that when you're looking at reducing an asymmetric or unsymmetrical ketone, we're going to see 2 different possible products result. So here's the second of our reducing agents that we're told are used. We have our H source, our hydride source from lithium aluminum hydride. So again, we see instead of a ketone, now we have this aldehyde, and it has been reduced using LAH, the abbreviation for our lithium aluminum hydride, in a water solvent. So we see a yield here of about 86% for this alcohol. So there's a comparison that we can make based on the hydride, the H negative source, um, that can result from either LAH or sodium borohydride. So this LAH, this is much more reactive of a compound than our sodium borohydride. And we can see here that we could not use this in the form of a protic solvent because it would react with the solvent and deprotonate that um, as well. So we have this reaction here, the mechanism shown, this source of hydride, again, it attacks that slightly electropositive carbon, and we see the breaking of this pi bond, the electrons shifted, and we see this alkoxide intermediate product that's formed, and then in our workup step here, we can protonate that using hydronium. Um, so our proton source, rather, it has to be added after our carbonyl is reduced. So we cannot use that type of protic solvent. And then we see a similar product that results to our sodium borohydride reductions. So if we wanted to make sure that we generated an alcohol through a compound that has two sites, two functional groups that could react. We want the carbonyl to be reduced and not this pi bond shown down here below. So we're told that hydride delivery reagents would be selective for our carbonyl, such as our borohydride here or our lithium aluminum hydride down below. And we can see that the alcohol is reduced, or I'm sorry, the carbonyl is reduced to an alcohol where the alkene is left untouched. Whereas if we try to do a metal catalyzed hydrogenation, shown on the left-hand side here, it would do both, right? We would have this group uh, reduced rather, this becomes an alcohol functional group, but also our pi bond will be lost. So if we don't care, we could have both react and we would have a similar high yield to that of our other reducing agent pathways. So the reactivity can be fine-tuned or reduced or increased depending on which R groups are on our reducing agents, our hydride delivery agents, rather. So we have our lithium aluminum hydride over here, but if we change those hydrogens to R groups, such as alkoxides or cyanodes, functional groups, we can increase or decrease the functionality. More sterically hindered groups, so maybe something like a tert butyl, could also affect functionality. So if we have a carboxylic acid or an ester, we could use lithium aluminum hydride to reduce these types of substrates as well, these types of starting materials to alcohol. So you can see the same reagents used, excess LAH and water in both of these processes, but they have slightly different mechanisms of action. So let's take a look here. In the reduction of an ester, we would need two equivalents of our hydride because we generate, after the first step, right, we break that carbonyl, that double bond, and generally methoxide is not a good leaving group, but it acts like one here because it's a very high energy intermediate here, and then it becomes this more stable aldehyde that I circled there. So the carbonyl reforms, so we need that second hydride delivered to reduce it again. So we have, again, a nucleophilic attack, loss of leaving group, and then reformation of that carbonyl. And then we have one more nucleophilic attack by our hydride. And then we have that workup step at the end where we we generate our alcohol by adding a proton source. And that gives us our final product.